I'm Dr. Andy Turner, and I'm going to tell you about some of the results of our BITMAP project that's been running for the last few years and finished recently. BITMAP is better understanding of interregional teleconnections for prediction in the monsoon and poles. So the BITMAP project was funded under the Belmont Forum and JPI Climate 2015 Collaborative Research Action on Climate Predictability and Interregional Linkages. It's a partnership between the University of Reading, the Universität Hamburg, and the National Centre for Medium Range Weather Forecasts in India. You can see members of the project team there at Reading: Kieran Hunt, Len Shaffrey, and myself; at Hamburg, Robert Boschi and Valerio Lucarini; and at NCMRWF, Ashish Mitra, A. Jayakumar, and E.N. Rajagopal. Most of the work I'm going to show you in the rest of this talk is going to be from Kieran Hunt. BITMAP participated in 2 of the call's 3 foci on understanding past and current variability and trends of regional extremes, and predictability and prediction skills for near-term future variability and trends of regional extremes. Due to the nature of the funding, we were not able to design work on co-construction of near-term forecast products with users. All of the results from this talk can be found on our website at bitmap.monsoon.org.uk. So we were motivated to study western disturbances because these are at the junction between the extratropics and tropics at the north of the monsoon region of South Asia. Western disturbances were traditionally thought of as prevalent in winter and spring in northern India, and they feature a winter precipitation peak rather than being driven by the monsoon. However, there is anecdotal evidence of western disturbance-like features bringing extreme rainfall during the summer monsoon season, such as the Pakistan floods of 2010 or the Uttarakhand floods of 2013. And a wider motivation for this project is what will happen to western disturbances in the future, given that we expect the temperature gradients and moisture gradients on which the subtropical westerly jet sits to change. So to study western disturbances, we needed to define a tracking algorithm. The details are here. I'll not go through them in detail, but you can see our publication there in the Quarterly Journal of the Royal Meteorological Society for more information. And when we perform this tracking algorithm on reanalysis data, such as the ERA interim, we find more than 3,000 tracks since 1979 in that data set. And you can see a map of those tracks here, emanating from as far away as the Atlantic sector, but really clustering over South Asia. And we've got a red box there just to the north of India and Pakistan. That's going to be our focus region, and most of the rest of the diagnostics you'll see pertain to information in that box. Firstly, just to look at the seasonal cycle of western disturbances, you can clearly see there is pronounced seasonality with far more of these events in the wintertime. We also looked a bit at the vertical structure of western disturbances based on these 3,000 events. You're looking here at cross sections in the vertical with longitude through the center of an event on the x-axis and pressure height on the y-axis. Just looking at 3 of the fields in particular here. First of all, the meridional wind anomaly. You can see clearly the circulation, the cyclonic nature of these events. Next, looking at the vertical wind anomalies, you can see ascent ahead of the western disturbance and descent behind it as it moves eastwards. And then finally, in the temperature structure, you can see an upper level warm anomaly and a lower level cold anomaly, suggesting this thing has a baroclinic structure to it. We also wanted to ask, well, what happens to these western disturbances between years? Are there any interannual controls on their variability? Given that they sit on the jet, we might reasonably expect that if the jet moves its position or if it strengthens or weakens, then the numbers of western disturbances would also change. So this diagram just shows winter, but we found a clear signal that western disturbances are much more likely when the jet is shifted to the south. So that's the blue region over South Asia here. So when the subtropical westerly jet is shifted further south, we get more western disturbances. We also wanted to see how western disturbances behaved in the coupled model intercomparison project. So these are the typical GCMs used for climate projection. So we tracked all of the western disturbances we could find in the historical experiments of the CMIP5 database, and noted two main things. Firstly, we captured the strong seasonality of western disturbances, such as the winter storms, which are in the blue colors here, occur far more often than those during the summer months, by about 3 or 4 times. The other thing we noted was that most of the models, so these are all listed in black here, they tend to give slightly more storms, both in winter and summer, than in the observed estimate, which comes from the interim reanalysis. So next, we looked at what might happen to western disturbances in future climates. So we looked at the RCP 4.5 and 8.5 scenarios of CMIP5 out to 2100. And this time series shows what we found. The RCP 4.5 is the green, the RCP 8.5 is the red, and the multi-model mean is shown in the thick line here. In both these scenarios, we can see a clear declining trend, and we've tested this. It's statistically significant that there'll be fewer western disturbances in future climates due to global warming. So in summary, and offering a bit of an outlook, western disturbances are an important classification of storms which mainly affect northern India and Pakistan in wintertime. We made a composite of western disturbances based on more than 3,000 events from era interim and revealed them to have a baroclinic structure. We found them to be strongly coupled with the subtropical westerly jet, and of course that jet moves with the seasonal cycle and the development of the monsoon, which helps explain the different numbers at different times of the year. On an interannual basis, a southward displacement of the jet also yields a greater count of western disturbances. Western disturbances are responsible for heavy rainfall events, but they don't provide the moisture themselves, they merely redirect it, and most of that moisture comes from the Arabian Sea and Bay of Bengal. There's a clear signal of declining western disturbances in future climate scenarios, and that has potential implications for water resources, particularly in agriculture. And coming out of this project, we're left with further questions, particularly about the nature of extreme events in the summer, when western disturbances may be interacting with monsoon lows and monsoon depressions. Finally, it would be great to do some further work targeting the implementation of our tracking algorithm in real-time forecasts produced by meteorological offices around the world, such that they could issue alerts through web products about when western disturbances might occur, and therefore when they might bring extreme rainfall. I haven't talked about all of the work we've done, but I'll leave you with our list of publications arising from this project, and all of our tracking data sets are also freely available on the UK's Centre for Environmental Data Archive website.